In the description of this video is a link to a spreadsheet here that you can use to practice some of the ideas that I'm going to discuss in this video. And this video is about capacitors. And capacitors come in a variety of shapes and sizes with different values. So we need to talk about what a capacitor is and what it does. Did you know that if you have a circuit board like in a computer or something and it blows up or fries, very often you can fix it yourself by going in and changing the capacitors. There was too much voltage on there and the paper and the material that's in there evaporated and kind of blew up. Maybe you won't see this residue on there so much, but you might just see the capacitor bulging. In fact, they put little creases in the metal there so that if it does get too hot inside, it doesn't explode. It can release that pressure under a controlled manner. But if you see them, certainly if you see the residue there, or if you see them bulging and particularly cracked like that, you know that the capacitor is bad and you can order a new one. All right, so what is a capacitor? Well, like I said, they come in a variety of shapes and sizes, but the simplest one is a parallel plate capacitor. And we've done some things already looking at parallel plates. One of the things we did was looked at the electric field between parallel plates. So there's going to be a lot of information on this screen here, but we'll try to explain as we go. So first of all, electric field was by definition how much electric force there was per charge. That's the definition of an electric field. Okay, and then we had that the electric field was also how many field lines there were in a given area. So there would be 1, 2, 3, 4, 5, 6 field lines in that area, and the strength of the field would be proportional to the number of field lines in a given area. Okay, so if two things are proportional, we can set them equal to each other if we drop in the right proportionality constant. And that proportionality constant is called the permittivity of free space. We call it epsilon sub naught. And the permittivity of free space is just how well empty space permits electric fields to get set up. So if this is a vacuum, this is going to have a certain value. And if it's air, it's nearly the same value. So we usually treat that the same as it is in a vacuum. One of the things that's interesting is the number of field lines is exactly equal to the number of charges that are on those plates. There'll be one field line for every charge. Q is for charge. So if we rearrange that and solve for the electric field, we can calculate the electric field between here, how much force there is per charge. If we know how many charges are on there, the area of those plates, and the permittivity of free space. Okay, and that's an equation we also have on our equation sheet. We also remember that work is force times distance. And the amount of work that we did moving the charges from one plate to another would equal the change in the electrical potential energy. And that would be the electrical force times the distance. Just work is force times distance. Well, if we rearrange this equation, the electrical force is going to be the amount of charge times the electric field. So charge times the electric field times the distance would give us the electrical potential energy. If we divide both sides by Q, that would be energy per charge, which we recognize as voltage, or a difference in electrical potential. And then if we just solve that equation for the electric field, we have that the electric field is the difference in potential divided by the separation between those two things. And that's an equation we have on our equation sheet as well. Well, this calculates electric field, and this calculates electric field, so let's set those two things equal to each other. So we see Q over epsilon sub naught times A equals delta V over D. Now, this is just the area of the plates, and this is the separation of the plates, and this is the permittivity of free space. If we just eliminate those out of the equation, we wouldn't be able to say that these two are equal anymore, but we would still be able to say that they're proportional. So we're about ready to define what we mean by a capacitor, and then in particular capacitance. One thing we see is that the amount of voltage, the difference in potential on those two plates, is directly proportional to how much charge is on those two plates. If I had twice as much charge, I'd have twice the electric field, I would have twice the voltage as well. So the more charge you put on there, the more voltage you get. Those two things are in direct proportion. And if two things are directly proportional to each other, we can set them equal to each other if we drop in the right proportionality constant. In this term, or in this case, it is the C. We're going to call it C. And we can solve for C by dividing both sides by delta V. And C stands for capacitance. Okay? Now, capacitance is unique to a particular physical situation. For example, if the area of these things changed, the capacitance would change. If the separation between those changed, the capacitance would change. And if I had different values of this instead of free space, maybe I put other things in there, it would also change the capacitance. But if we have all the physical constraints constant, the ratio of how much charge is on there to how much voltage is produced is the capacitance. So capacitance would be measured in coulombs per volt. And if we have 1 coulomb of charge producing 1 volt of potential, we would say that is equal to 1 farad. And a farad is a unit of capacitance. It's 1 coulomb per 1 volt, and it's named in honor of Michael Faraday. We rearrange that equation, and in our equation sheet, we have it like this, that the difference in potential is how much charge is on those plates divided by the capacitance. Just rearranging that. Okay, let's come back to this up here. If I cross multiply just that part, so I'm going to multiply both sides by this, I'm going to divide both sides by that, that will rearrange and give us this. Okay, but charge divided by voltage is the same thing as capacitance. So it looks like the capacitance is equal to the area of those plates, the separation of those plates, and the permittivity of free space. I just put that out in front. I do have a K here. That's called the dielectric constant. What it means is if we put something in between there other than empty space, like we put paper there, or plastic, or glass, or something like that, it's going to change that constant by some factor. All right, so we've got 5 equations. This is also on our equation sheet. So let's see if we can just get a little a practice using these 5 equations. So here I have a parallel plate capacitor, and I have it hooked up to a power supply with 9 volts. And one of the problems we have done is sending a charge through an electric field. So knowing the strength of the electric field and the value of this charge, I can predict how much force is on that charge. But I can calculate the strength of the electric field by just knowing that it was 9 volts, and then I would have to measure the separation between those two things. Okay, so voltage divided by separation would be electric field, and electric field multiplied by the charge of a single electron in this case, would give us the force on that electron. All right, now let's look at this one. We have changed the separation. So what is that going to do? We still have 9 volts of potential between those two plates, but we have a larger separation. A larger separation would say that we should have a weaker electric field. But let's not try to understand why that would be if the voltage was still the same. Well, here, talking about capacitance will help us to understand that. A larger separation would make it have a smaller capacitance, a smaller ratio of charge per volt. And a smaller capacitance, if we have a smaller capacitance and the voltage stayed the same, we still kept 9 volts on there, it would take less charge. Smaller capacitance would be a smaller amount of charge to get the same amount of voltage. So by separating these two things and keeping 9 volts on there, there's actually less charge on those plates than there was when they were close. You didn't need as much charge to get the same amount of voltage. Well, less charge is going to be a weaker electric field, and a weaker electric field multiplied by the charge of this electron would be less force. Okay, so that's just kind of putting those equations all together here. This here is a capacitance meter. It is measuring the capacitance in this situation. And remember, capacitance is charge per volt. So to measure the capacitance, it must know how much charge is on those plates and the voltage, the difference in potential between those two plates. Okay, so right now I have 44.2, and the dial is set right there at picofarads, 10 to the minus 12 farads. And these are really close. But if we change the separation, a bigger separation should be a smaller capacitance. So it was 44.2 before, we had a bigger separation, and you can see the capacitance went down. And if the charge stayed the same, if there was charge on these two things, if that stayed the same, a smaller capacitance means there's a bigger potential difference between those, because we're separating those things. They're attracted to each other. We had to push them apart, doing work on those charges. We've given them more energy per charge. Separating them even more, the capacitance went down. Separate them a lot, the capacitance went down even more. Okay, now I'm back to that original situation here, but this time I have paper here. I'm just going to slide a stack of paper in between there. I'm not going to change the separation, so this is the same. I'm not changing the area of those plates because they're just cut out pieces of metal. But what I am going to do is change the free space in between there. It's not free space anymore, it's paper. So when I put the paper in between there, the capacitance went up. Okay, so that means that paper has a bigger permittivity than free space does. And it went, let's say it went from 40 to 60. That means this number must have been about 1.5, because 40 times 1.5 would get us up to about 60. Just rough numbers. Okay. This is another type of capacitor. It's a variation of a parallel plate capacitor, but it's a variable capacitor as well. We're changing the capacitance not by changing the separation, but by changing the overlapping area. So these plates are going to have one charge, like a positive charge. These plates will have a negative charge. So right now they're only overlapping a little bit, but if we turn this dial up here, here's the area in which they're overlapping. So by changing that dial there, we're increasing the area, which increases the capacitance. And if the charge on those plates stayed the same, a bigger capacitance would be a smaller voltage. This is used to dial in different voltages on a circuit. Okay, so here that is swung around, and these plates are now overlapping in a very large area. Some other examples of parallel plate capacitors would be just your keys on the keyboard. under the key is a metal plate, and then there's another metal plate here. Those two metal plates have charge on them. And then there's some sort of like plastic rubbery material that changes the constant out in front there. It's going to be different than just the permittivity. It's going to be different by some factor, and it's called the dielectric constant for that material. But if we push this key, we reduced the separation for a moment. A smaller separation changes the capacitance, makes it bigger. So a bigger capacitance with the same amount of charge on those plates is going to decrease the voltage. And that change in voltage is sensed by the computer to indicate that that key was pressed. Another way capacitors like this are used is with what's called a condenser microphone, where sound comes in here and these compressions and rarefactions hit the plate here and it causes that plate to vibrate. Well, we're just changing the separation between these two plates. Changing the separation changes the capacitance, changing the capacitance changes the voltage, and we're keeping the charge on those plates constant. So that's going to create a signal that you can record. There are other types of microphones that use magnets and coils of wire, but that's coming up when we talk about magnetism. Now, this equation here, the capacitance is the dielectric constant times the permittivity of free space times the area divided by the separation. That situation is for parallel plates. Okay, this is called a Leyden jar, and it's not quite this situation. So it's not going to be quite this equation that calculates the capacitance of this. But this thing, if you've ever played with a Leyden jar, it will knock you on your butt. Okay, here's what happens. There's this metal jar here and a plastic container, which is a dielectric, which is made out of some dielectric, and then another container, and you put all those in there. I'm using my capacitance meter to measure the capacitance of there. And again, it's on the picofarads, so that is a pretty small capacitance. So if I bring this close to a Van de Graaff generator and let some electrons jump from the Van de Graaff and jump onto here, if I put a fair amount of charge on that and it has a really small capacitance, we're going to get a huge voltage, a difference in potential between those two things. And then when someone's holding this thing and then someone else touches that thing and they complete the circuit, wow, those charges can dash through your body very quickly. All right, something else that capacitors will do is they can level out and smooth out noise in an electrical signal, or just smooth out the electrical signal. It will turn something from alternating current, going back and forth 60 times a second, into direct current, just staying the same voltage. Our wall outlets use alternating current, batteries, direct current. So I have an oscilloscope here and I'm analyzing the voltage coming out of my power supply. So it's positive for a bit, then negative, positive, then negative. And this little device here is not a capacitor, it's called a diode. It's a one-way valve for electricity. It lets current go one way, but when it tries to go the other way, it just stops it. It prevents it from going one direction. So if I take this alligator clip and I clip to the other side here, it's going to stop the current from flowing when it's trying to flow the other direction. So alligator clip moved there, and instead of the voltage going negative, it just stopped it. Okay, that was the first step in turning alternating current into direct current. Put a diode in there. Okay, now this is a 4.70 nanofarad capacitor, and I'm putting it in parallel. I'm not going to go into a lot of detail on this, but it takes time for the capacitor to charge up, and it takes time for the capacitor to charge down or to drain. And here we're seeing that with the capacitor in between here, it charged up, but it didn't drop immediately and then go flat like it did here, drop and then go flat. It took more time to drain out before the voltage of the power supply was trying to shoot it up again. If I put a larger capacitor in here, it's going to take more time to flatten out. And I should say that the RC here stands for resistance and capacitance. So if I knew the value of the resistance and I could know the value of the capacitance, we could find what's called the RC time constant. That does go into a little bit more detail than what you would typically see in AP Physics 2. All right, let's put a really big capacitor in there, and you can see that it just flattened out. It didn't have any time to spike up and down. And that's what capacitors on circuit boards do. They level out the noise that might be created from other circuits nearby. Okay, another thing that capacitors do is they store energy. So if you had a flash on a camera and you wanted that to burst and give a ton of light out at one time, batteries can only produce voltage over a length of time. It can't like burst out all this power. So what the battery does is it charges a capacitor over some time. And then when you click the flash, all that stored energy can now go into the flash and burst out all that energy in one moment. So the capacitor is necessary to store energy. So let's talk about how much energy it stores. If we start out with no voltage on the battery, we aren't going to have any charge. But we should see a linear relationship between potential and voltage. Potential and charge. Okay, because for a particular capacitor, it's directly proportional. Twice as much voltage should get us twice as much charge. Okay, so voltage was how much electrical potential energy there was per charge. That was the definition. And then we just rearrange and we can calculate the electrical potential energy by taking the voltage multiplied by the charge. Take this voltage multiplied by this charge. Well, that sounds like the area under that curve. This voltage times that charge, although we do have to divide by 2 because it's going to be an average charge. It's a triangle. 1/2 base times height. So we're not talking about like a point charge. We're talking about a large amount of charge. So we use capital Q. But it is just 1/2 base times height. 1/2 base times height would be the total amount of energy it took to charge that capacitor. So when you have 4.5 volts on there and a little bit more than 4 coulombs of charge, multiply those two, divide by 2, that would be the total potential energy of our capacitor. And then remember that capacitance or charge is going to be the same thing as the capacitance times the voltage. So charge, we're going to substitute in capacitance times voltage, and we would get capacitance times voltage squared. Okay, and that's an equation that's on our equation sheet as well. Okay, so we've checked off quite a few, but just if I know the total amount of charge on the capacitor and the potential difference, I can calculate the energy. Or if I know the capacitance and its voltage, I can also calculate the potential energy of the capacitor. Okay. Another situation that capacitors could be in is this spiral effect where we have a metal plate here and a metal plate here and then separated by some dielectric. And that's what these capacitors are. If we pull off that covering, we see we have metal here, and they're separated by this dielectric paper. And again, this equation was for parallel plates. It's not the right equation for this situation, but it gives you an idea that these are physical descriptions of this area and separation. So the capacitance of this is going to be some fixed amount. And we can see right on here that this was, it was 220 microfarads. 220 microfarads is the value of the capacitance for that capacitor. So if we know the capacitance and the voltage, we can calculate how much charge is on there. Okay, so these are the type of capacitors we see in circuits like this. Now for the lab. Basically what we want to do is see if this equation holds. Okay, see if the voltage and the charge really does produce a constant capacitance. Okay, so to do that we have to measure the voltage, and we actually have to know how many coulombs of charge are on the capacitor at any moment. Okay, so we're going to do it a similar way that we did with flow continuity, where you had water in the cylinder and the water spewed out like this, and we could calculate the flow knowing the area of that hole and the velocity, or the area of that and its velocity down. They'll have the same flow. Okay, but the total amount of water in the cylinder at any moment can be found if you know how much water leaves the cylinder each moment until it's empty. Okay, so we can calculate how much water is in there. We're going to make an analogy with the amount of charge on a capacitor. We can calculate how much water is in there if we know how much water is leaving every moment until there's no more water in there. What we're doing is just finding the area under that curve. Okay, knowing how much water is flowing out for this period of time and how much water is flowing out for this period of time, all the way until it's empty, I can keep track of how much water has left the cylinder, so I would know how much water was in the cylinder at any time. If I want to know the amount of water at 8 seconds, I would just figure out how much water has left from 8 seconds to when it's empty. Okay, so here is our lab. We don't know the charge on there, but I am measuring the current. Okay, I have a current meter that will plug into the computer and give me the current at every value of time. I will also know the voltage on that capacitor for each of those values of time. So I'm trying to calculate the capacitance of this. I need to know the voltage, that's here at any moment, but I need to know the charge on there. And I can do that by keeping track of how much charge has left the capacitor each moment. I think that's all I want to say about that. I don't want to give away the answer, and I do not have a video that walks you step by step through this. I'm leaving you on your own for this, but you've learned a lot in AP Physics 1, so you're ready for this now.